finally we arrive at the last presentation. Let's say this is a presentation about something different from what we have seen so far, because the presentation is not about a meteorological model, but a model that is in between the meteorological model and the hydrological model. It has been studied and developed for generating high-resolution rainfall precipitation fields, because sometimes we need a very high-resolution precipitation field in order to properly reproduce the discharge hydrograph in the basin we are considering. For instance, the Bisagno River we are considering is a very small catchment, only 100 square kilometers. And if we use directly the numerical model, maybe we underestimate the total discharge we have. The other thing is that with this model, even if you have a meteorological model at very high resolution, with this approach you can basically generate an ensemble of field, of precipitation field, in basically maybe 100 of fields in 1 hour or less, so on a quite big domain. So this is a stochastic approach, is not a numerical one, do not follow the rules of the meteorological model, but is more, let's say, a post-processing we can do of the meteorological predictions. So this is the publication of the model. So basically what at the beginning we need, when we want to make prediction properly, we need to be very consistent with the spatial temporal scale we are using for the input of hydrological models. For instance, in this case, we have a river of 300 square kilometers, and we have a precipitation input with a temporal resolution of 5 minutes, but with spatial resolution increasing from 16 by 16 kilometers up to 1 by 1 kilometers. And you see, if we use let's say the coarse or spatial resolution, we do not properly estimate the discharge, that is the black line. Only if we are at 4 by 4 or even less spatial resolution, we are able to do this kind of prediction. The same if we consider that in time. We need to, if we have a resolution of, let's say, 3 hours, this resolution is too coarse for our catchment. We need at least a resolution of 1 hour to be able to properly reproduce the peak discharge. So at the end, we have to consider this when we are not only running a meteorological model, but try to build up a complete chain. This is a very complete stuff. So starting from the ensemble prediction system, local ensemble prediction system, downscaling, hydrological modeling, and then you have like a spaghetti plot of hydrological response of the catchment. So in this talk, of course, we will talk more about this kind of approach. Maybe, since it's very late, I will not go really in detail of the equations, but I try to give you a general flavor of the model. Of course, if you have questions, I'm here, so please, we can talk also tomorrow or later. So basically, in literature, there are many downscaling models, many approaches that show you how to increase the resolution of precipitation in a stochastic way. Our model, our approach is important because for two reasons. The first one is that it conserves the correlation of meteorological rainfall fields both in space and time. So it actually takes into account some of the features of the meteorological model, so some of the features that belongs to the physical processes. The other one is also that conserves the position of larger scale structures. You do not say, okay, rainfall inside the blue domain can be there, or there. It just preserves the precipitation where at large scale is. And this is important when you have the effect of the orographic effects, for instance. So the model is not able by himself to try to model, but in this way it preserves what the large scale of the meteorological model and try to put down to a smaller scale. So basically, and in this part I will go very quickly, so we start from the meteorological prediction aggregated to a reliable scale, so a scale in space and time where we are confident in, and do the gaussianization of the field. So the precipitation field is not a Gaussian field, but let's say in order to follow and to properly transform with the Fourier transform, we need to make a Gaussian transformation. So basically, we do this kind of Gaussian transformation. Starting, let's say, this is the PDF of precipitation, and this is its Gaussian transformation. Then go in the Fourier space, and basically what we are interested in is the power spectrum that many of you know of the prediction. Of course, this is a power spectrum only in time, but it's only 1D. But you imagine a three-dimensional power spectrum. This is only 1D for showing you let's say in a better way. So basically, all the scale, so let's say maybe from 300 kilometers up to 16 kilometers in space, and from 12 hours up to 3 hours, are the scales that can be resolved by your meteorological model. If you calculate the power spectrum, the shape is this one, and then you want to go from 16 kilometers down to 1 kilometer and generate an ensemble of maybe 100 fields at 1 kilometer scale. So you still need some information. The thing is, maybe some of these scales, also those resolved by the model, are not so reliable because of numerical problems. So basically what we did is just set the reliable scale of our model, estimate the power spectrum on these scales, then extrapolate the power spectrum on both the unreliable scales and on the downscaling scales. So basically we have a brand new power spectrum following a power law, a three-dimensional power law, like you can see that the equation is this one, but using random phases. So basically you put the precipitation here and there without caring too much where the precipitation is going. So there are two free parameters, the exponential, so how in space and time is organized and is correlated the precipitation. You use random phases, and then you go back to the real space, this time at a very higher resolution, let's say before was 16 kilometers and 3 hours. Now you have maybe one field alone. Now you have hundreds of fields with a spatial resolution of 1 kilometer and temporal resolution of maybe quarter of hour. Then you go back in the physical space because it's a Gaussian field generated. Then you go back to the precipitation field by exponentiating this field. This is really simple. And basically at the end you force with a normalization the synthetic field to be equal to the original meteorological field when aggregated to some scales that you consider reliable from the meteorological point of view. But the good thing is the RainFARM approach, that you can choose a different set of Fourier phases, and in, let's say, in very few time you can generate an ensemble of fields that at larger scale are all the same field, and I will show you the figure later, but at small scale they have different features. And this is very important, especially when we are dealing with hydrological prediction. So when the distribution of precipitation in space and time is really important, but because it can make the difference between a really dangerous events like Professor Sicardi showed you this morning, to the event with a total amount of precipitation, with an equal amount of precipitation over 24 hours, but a different distribution, let's say, in time. So these are the parameter of the model that you can set, and there are few parameters. So basically, the idea is that this is the one meteorological model. You can use the downscaling mode approach, that is basically say, okay, the rainfall can fall everywhere in the domain, and this one is try to put the rainfall in the same place of the meteorological model. This, just to show you more on the feature of this is the NWP model precipitation, the precipitation predicted by the numerical weather prediction model. You see, is a very coarse resolution, is 16 by 16 kilometer. This is downscaling only in space, just to show you the effect. When we downscale, then we start changing 8 by 8 kilometer resolution, 4 by 4, 2 by 2, and 1 by 1. So with the downscaling model, we just pass from this one, that is that's a uniform prediction inside each grid point predicted by the meteorological model, to one possible realization of distribution of precipitation inside this value predicted by the meteorological model. And I will show you, this is, let's say, a movie of how the model can work. So here you see the warp field with a resolution of 10 by 10 kilometer in 3 hours, and here the resolution is 1 by 1 kilometers and 0.25 hours. You see, the scale is the same, is in intensity, because so they can be compared easily, and and hopefully I will go there and see. Okay. I forgot, but I will show you later. So I forgot to copy the part of the, anyway, I'm sorry. because it was on the pen drive, but it was is not. So here, and maybe I want to, tomorrow I will show you this slide and this movie, because basically you see here the prediction made by the Wolf model and the prediction made by one realization of the downscaling field. So let's say this is the spatial example I want to show you in a movie. Let's say this is a delimited area prediction field. So we upscale to 16 by 16 kilometers. So all these fields are the same. Then we start with the downscaling. Each story is the downscaling model. As you see, at the, let's say, this scale, all the models are the same. So you start from exactly from the same precipitation amount and precipitation distribution at this spatial scale, and then each one is, due to the random phases we are using, each one is generating a small scale distribution that is really different. And this is important, especially, well, as I said before, for the catchment you have underneath. So basically, what we did, and this is the experiment we did for validating the model, is starting from the precipitation observed by radar, upscale to the resolution of 16 by 16 kilometers and 2 hours in time, and then forgot about the radar precipitation and downscale from this field down again to 1 kilometer by 1 kilometer at 0.5 hours. That is the same resolution of the radar. And you see, okay, it's not exactly the same because as I told you before, it's a stochastic approach. So you have to generate more, not only one realization, but an ensemble of them. But is able to generate exactly the same structure of precipitation you have at high resolution. So this is let's say, it is not important from a meteorological point of view, but let's say when you start working the coupling meteorological models and hydrological models, then you need to take into account this thing. So this is on the x-axis you have the rainfall intensity, while this is the PDF from, let's say, the green one is of the radar image and the black one is of rainfall. So basically it's generating the same distribution of rainfall. And let's say, the black one is the distribution, let's say, the original field in time, like this gray area and the dashed line. The dashed line is the average, and the gray area is the distribution of the ensemble of average precipitation in time. And you see that the distribution is following exactly the same line of in the same amount of precipitation of the original field. Just, let's say, but you are able to generate in an ensemble way at very, let's say, this at sub-grid scale. So when you need to go even, let's say, a scale that are smaller than those predicted by your model, or you need to generate an ensemble in a very quick way, starting from a numerical weather prediction, but a single numerical weather prediction. So these are some statistics. So that's the idea, and let's say I want to be very brief because this is very late. But the idea of this model is just is here and is there the model to couple properly rainfall from meteorological model and hydrological model in order to be sure that the scales needed by the hydrological models, that are maybe the Bisogno river is 100 square kilometers. So 100 square kilometers means that the resolution of 10 by 10 kilometer of a numerical model is not enough, because we have basically 1-2 grid point of average precipitation. So you need to increase the resolution of your numerical model. Or if you have, or maybe you have a resolution, a numerical model resolution of 5 or 1 kilometers, but in this case you can easily generate an ensemble without running a lot with your model of meteorological model a lot of time. So the theory was shown before. Now, how it works on the DRIHM portal? Basically, there is a bunch of Python files that drive the model. Needs very few data, just the domain where the model is working as a static data, and then some source data that derives from a meteorological model. For instance, Worth model that has been described before by Elizabeth. And then you get the settings and the geographical data, that is the domain and the digital elevation model needed. So all the data, the static information that are read, then you have the P interface and reading the forecast data, but in NetCDF, I forgot the F. So from a meteorological model, and then you run properly the RainFARM model with these two kind of Python code, driver and model. It generates the high resolution ensemble forecast data, and then save the data again with the P interface. So is a standard interface. You can basically the data of precipitation are written again in a standard format, and then they are stored and saved to be used directly in an hydrological model. So from the portal configuration, basically you choose create ensemble output, you put the RainFARM. Now you cannot do it alone. You actually need or a numerical weather prediction model to start with, or it's an hydrological model to use the output of RainFARM as input for these models. You put the number of stochastic ensemble realization. For instance, in this example, say, okay, I want to run it 100 times. The increasing factor for the spatial resolution, let's say 10, means that the resolution is 5 kilometers. Then I will go to fields that have a spatial resolution of 500 meters, so very high spatial resolution. An increasing factor in the temporal resolution of 6 means that if I have 3 hours as time resolution, now I have half an hour as temporal resolution. Now I have half an hour as temporal resolution, and you can submit the job. the job let's say, give you the results depending if you are downscaling a meteorological model or using the downscaling approach to run with the hydrological models. You will, of course, will have different results. You can also upload an end list. So, okay, upload the data from previously done ensemble, and just put the NetCDF file with the meteorological information, the initial time of the simulation, the end time of the simulation, the number of stochastic ensemble you want to generate, the increasing factor in space, and the increasing factor in time. And then you can run also in this way your models and obtain results from the downscaling. So that's it. I think that's it. For now it is happening. Tomorrow maybe I want to show you the video showing the differences between the meteorological model and the hydrological model application, the downscaling model application, if I'm able to find it inside my computer. Okay, thank you. So, if you have no question, we can go.
Just one comment.
Yeah.
Because RainFARM was running on Ford ARW before this project. What we did during this project is after standardization of the messages to run RainFARM or Ford.
Yeah. Yeah, let's say in this before was just coupled with one specific meteorological model, and now it can be, in principle, can run with our own or also with the meso-image. So all the meteorological models you have seen now through the P interface can, let's say, can be coupled with the RainFARM and with the hydrological models. Yeah. Okay. Oh, question?
Yeah, the number of the downscaling is a matter with the solution of the model, whatever is the resolution of the end of the.
Yeah, let's say the matter of downscale depends on the resolution on numerical weather prediction model, but also on the catchment you are considering. Because if you are considering very small catchment, maybe your numerical weather prediction model can spend a lot of time to run for maybe just one very high resolution output. In this way, you can maybe run your model at higher, let's say coarser resolution. You spend less time in running it, and then use the RainFARM for do the other job and have very high resolution ensemble. Because my opinion is that even if you go very fine with the spatial resolution, since you need to run the model, the initial condition at the same very high resolution in order to give you exactly a proper prediction. So maybe sometimes it's better to run the model, the meteorological model at less, not very coarse resolution, and then say, okay, it's like an admission of ignorance. I don't know actually what happens at 1 kilometer scale. So is almost not very useful to run your meteorological model at such fine scale, and then you spend a lot of time, a lot of computational resources, and you have the proper prediction. But it's better, let's say, to stay a little bit at coarser resolution, and then for precipitation, of course, start with this kind of approach that in maybe 1 hour you can generate 100 of possible realizations. So like the talk of Professor Sicardi this morning, 100 of possible words where you can actually estimate which is the probability of having one type of Grandi factor. No, that's the idea. Okay?